This course is about troubleshooting residential and light commercial irrigation systems. You can think about an irrigation system as being composed of two systems working together. The first, a mechanical system that carries water from the point of connection and distributes it onto the lawn. And the second, an electrical system that carries information from the controller to the mechanical system and tells it when to turn on and off. This course will focus on the mechanical components, sprinkler heads, valves, and pipe. We'll discuss how to diagnose common problems with each of these components and how to solve these problems quickly and efficiently. The most common irrigation system problems associated with the sprinkler head are coverage problems, leaks at individual sprinkler heads, and obvious sprinkler failure. We'll discuss each of these in turn, identifying the symptoms, discussing the potential causes, and recommending a solution. Symptom number 1. The turf is stressed due to inadequate or uneven water application. This can take the form of rings, dry areas, stressed plants, and other evidence of patchy water application. If the turf is stressed, something is preventing the water from reaching its destination as it was designed, or should have been designed, to do. The first thing to check for are physical obstacles that might be getting in the way of the water. A common problem with older systems is that the sprinkler heads sink into the ground, causing the head to be too low to deliver water effectively. When you turn the system on, look at each sprinkler head to make sure that it clears the turf. If the heads are low, you will need to reset the head to make it level with the base of the turf. Sometimes you can raise the head simply by adding a threaded male adapter between the swing pipe fitting and the threaded outlet on the bottom of the sprinkler head to create the additional height needed. Another potential problem is a change in landscaping that causes the original design to become ineffective. This can happen if new landscaping has been installed or if plant growth has caused obstructions not foreseen in the original design. A solution can be as simple as adding an extension to a spray head to help it reach over the top of a shrub. Sometimes you'll need to move sprinkler heads to address the issue. If there are no physical obstructions that explain the coverage issue in a rotor zone, check the nozzles on the sprinkler heads to make sure they are correctly sized for matched precipitation. Quarter circle rotors should have nozzles with half the precipitation rate of half circle rotors and a quarter of the precipitation rate of full circle rotors. Half circle rotors should have nozzles with half the precipitation rate of full circle rotors. If we consider this chart for K-Rain RPS 75 nozzles, we can see that if a half circle rotor is on the same zone as a quarter circle rotor and the quarter circle rotor has a number 1.5 nozzle with a flow of 1.4 GPM covering a quarter of a full circle, then a half circle rotor should have been a number 4 nozzle with a flow of a 3.0 PGM, about twice of that of the quarter circle rotor because it covers twice the area. Sizing gallon flow to the area of coverage will result in matched precipitation over the entire zone. If precipitation rates are not properly matched, you can easily address the problem by changing the nozzles. Be careful, though, to attend to the total number of gallons per minute on the zone. This should not exceed the maximum flow rate for the system. Aiming for approximately the same total flow rate with new nozzles as with the old ones will ensure that there is enough flow for the zone. For instance, if you have a zone with 2 quarter circle rotors and 2 half circle ones, all with 2.0 gallon per minute nozzles, you have an 8 gallon per minute zone. If you change the half circle rotors to a 4.0 gallon per minute nozzles, the zone becomes a 10 gallon per minute zone, which might be too high for the system. A safer choice would be to replace the quarter circle nozzles with a 1.0 gallon per minute nozzles to achieve matched precipitation, which creates a 6 gallon per minute zone and lowers the flow rate for the zone instead of raising it. If obstructions or matched precipitation aren't the problem, there could be a water pressure issue that is preventing the sprinklers from delivering water evenly over the area. To get an accurate reading of the pressure, you'll need to measure the operating pressure. To do this, a pitot tube is a helpful tool. It's essentially a thin metal tube that can be inserted directly into the stream of a sprinkler and attached to a pressure gauge to give a quick reading on the operating pressure at the head. Spray heads require an operating pressure of 25 psi and rotor works best at a 50 to 60 psi. If the pressure is too low on a single zone in a system, the zone might have too great a flow rate to maintain optimal water pressure. You can re-nozzle the zone with smaller nozzles to improve pressure. The smaller nozzles reduce the flow rate, and the lower flow rate reduces the pressure loss in the pipe. This is what increases the pressure available at the sprinkler heads. If you change the nozzles, be sure to increase the runtime for that zone to account for the new precipitation rate. If all the zones on the system display pressure problems and there is no visible leak in the system that might be causing the pressure loss, the water pressure from the city may be too low to operate the system. Contact the water purveyor to verify the water pressure on site, or use a hose bib gauge. If it is indeed too low, you can install a booster pump at the source to create an additional pressure necessary to operate the system. If there are no physical obstructions, the nozzles are selected for matched precipitation, and the sprinklers have enough pressure and are working properly, it is possible that they've been installed too far apart. Measure the distance between the heads to see if it is within the parameters for head-to-head spacing. For a typical residential or light commercial system designed with square spacing, this is equal to the published radius of the sprinkler, with the installed nozzle at the available pressure. To compensate for wind, it is typical to lower the spacing to 90% of the published radius. If the sprinkler spacing is a problem on a spray zone, you can change nozzles from spray nozzles to multiple stream rotary nozzles. This will both increase the radius and reduce the flow rate on the zone. If you are facing gear-driven rotors that are placed too far apart, you may need to add heads or a new zone to address coverage issues. Symptom 2. Water is leaking out of heads at low points in the zone. There are two common causes for water to be leaking at a sprinkler head at a low area on the zone: a problem with the sprinkler and a problem with the valve. If the leaking is intermittent and generally happens only after the zone has been run, the problem is usually the sprinkler head. When the zone shuts down, all of the water in the line running to that zone flows downhill to the lowest sprinkler, where it can leak out. To address this, add a check valve in the sprinkler. Manufacturers sell check valves separately or pre-installed in the check valve version of the sprinkler. So you can either unscrew the sprinkler head and insert the check valve, or just change out a check valve sprinkler for the non-check valve version. For larger elevation changes, you may need to add a separate check valve installed under the sprinkler. The in-sprinkler check valves are not always sufficient to prevent leaking in large elevation change situations. As a rule of thumb, you should install an under-sprinkler check valve on zones with elevation changes greater than 7 feet. If the wetting around the low sprinkler is continuous, the problem is more likely the valve. A weeping valve is one that is not fully closed, will generate a constant flow of a small amount of water that will find its way out through the lowest sprinkler in the zone. Open up and check for a damaged seat in the valve or a worn diaphragm. Repairing or replacing the valve will generally solve this problem. Symptom number 3. Water is leaking around a sprinkler head during operation. If water is leaking from a sprinkler while it's operating, the sprinkler has been damaged in some way. To fix this problem and prevent it from occurring again, you will need to address both the problem with the sprinkler and the conditions on site that created the problem. The first thing to check is the wiper seal. The sprinkler will leak if the wiper seal is cracked, worn, or has been damaged or scored by sand. Wiper seal problems are often caused by installing the head just a bit too low. When replacing the sprinkler head or the wiper seal, be sure to adjust the height of the sprinklers so it's installed correctly. The other common cause for leaks around the sprinkler head is the head-to-pipe connection. Check for leaks, cracks, or other breakage. It's also a good idea to try to figure out what caused the damage and how you can fix the sprinkler head to prevent damage in the future. If the connection has been broken by maintenance equipment or pedestrian traffic, you should install a more robust and flexible swing joint to absorb the impact when people or equipment run overhead. Symptom 4. The sprinkler head fails repeatedly when the zone starts up, the sprinkler or turret launches out of the ground. This kind of failure is an air hammer on the sprinkler created as the water rushes into the lines. Pressure can spike 3 or 4 times the pressure rating of the sprinkler head, damaging the sprinkler. There are 2 things you can do to address the problem. First, you can install a flow control valve that will allow you to regulate the flow to the line, making it low enough to prevent the air hammer from occurring, but not so low as to impede sprinkler performance while the zone is running. After installing the valve, start out with the flow control cranked all the way down, and slowly open it up until the sprinklers are operating optimally. The second thing to mitigate the issue is to install check valves in the sprinklers on the zone. This will keep the line from draining completely between cycles, eliminating the air in the line that causes the air hammer and pressure buildup. Problems with valves usually present themselves when a particular zone either will not turn on or will not turn off. Diagnosing these problems correctly requires a working sense of how a valve works. So, we'll start with a review of the inner workings of the valve, and then go on to discuss reasons that valves either won't open or won't close. There are two systems in a valve: the electrical system, where electricity from the controller energizes the solenoid, and a hydraulic system that opens the valve when the solenoid is energized and closes it when the solenoid is not. Let's take a closer look at how these two systems interact. First, let's review the parts of the valve. The base of the valve has an inlet side that plumbs into the main line, and an outlet side that goes to the zone. There's a rubber diaphragm that separates the inlet and outlet ports in the base from the chambers above it. It has two holes in it. The first is a metering system that allows water from the main line to pass through the diaphragm and fill the chamber above the diaphragm. The second is an exhaust port that allows water to flow out of the chamber above the diaphragm and into the zone line. The solenoid screws onto the valve. The plunger inside the solenoid, when not energized, is seated on the exhaust port. When the solenoid is not energized, the valve stays closed because as water flows from the main line into the valve, some of the water flows into the chamber above the diaphragm through the metering system, filling up that chamber with water. With the area above the diaphragm full of water, there is equal water pressure on both sides of the diaphragm. But the valve is designed so that there is more surface area in the chamber above the diaphragm than in the inlet from the main line below it. This presses the diaphragm down and seals off the flow of water from the main line, preventing any more water from flowing through the valve. The valve opens when the solenoid energizes. The plunger lifts and unseats from the exhaust port, allowing water to flow out of the chamber above the diaphragm, downstream to the zone line. There will still be water flowing into the chamber through the metering system, but water will flow more quickly out of the exhaust port. This eases the pressure on top of the diaphragm, which is then overcome by the water pressure coming in from the main line. Water from the main line then forces the diaphragm open, and water flows out to the zone. While the valve is in operation, there's always water going into the chamber above the diaphragm. It just goes right back out the exhaust port. When it is time for the valve to close, the controller stops energizing the solenoid, causing the plunger to drop and seat on the exhaust port. This prevents any more water from escaping from the chamber above the diaphragm. Water still flows into that chamber through the metering system, but now it can't get back out. Once the chamber is full, the water puts pressure onto the larger surface area on top of the diaphragm, causing it to close again. When there are valve problems, the body of the valve usually isn't the problem, but the internal components that do the work to make the valve open and close. The plunger, which must move freely up or down. The exhaust port, which must open and close without clogs or damage and allow the plunger to seat securely. The metering system, which must remain open to allow water to flow into the upper chamber of the valve. The diaphragm, which must seal properly. Now let's consider the most common problems with valves. Symptom 1. A valve stays on. This means that sprinklers in one area of the irrigation system run continuously except when the main water is shut off. In this scenario, the first thing to do is to verify that the problem is at the valve and not the controller. If the controller is continuously sending power to the solenoid, this would prevent the valve from closing. Using a multimeter to check at the controller if there is power going to that zone. If so, there is a problem with your controller. If the controller is not the problem is at the valve itself. Take off the solenoid and check to see if the plunger is hanging, or if it is moving freely. Debris can get into the solenoid and cause the plunger to get stuck, which will prevent the valve from closing. If this is the problem, rinse out the solenoid to free the plunger. The next thing to check is the seating of the plunger on the exhaust port. If the plunger does not seat properly, it won't stop water from the chamber above the diaphragm from flowing into the zone line, which would cause the valve to remain open. If the solenoid plunger is moving and seated properly, the problem is likely with the metering assembly or the diaphragm. Disassemble the valve to access these components. You can find the metering assembly on the diaphragm by looking for the small screen designed to prevent debris from getting caught. Rinse this thoroughly to dislodge anything that might have got stuck in there. Look for tears or other damage to the diaphragm that would prevent it from closing properly. Check to see if the seating surface is clean and undamaged. Once you have replaced any worn or damaged parts and reassembled the valve, check the zone with the controller to ensure that it is working properly. One small reminder, if this is a new system and everything inside the valve is working properly, but the valve still won't close, make sure that the valve is installed in the proper direction. A valve installed backwards will close once, but afterwards remain open. Symptom 2. The valve won't activate under power. If the valve won't open, the first thing to check is whether there is power at the valve. You'll need to check this in two places, at the controller and again at the solenoid. This will determine whether the problem is at the controller, in the wiring, or in the valve itself. Once you have determined that there is power at the valve, the most likely causes for the problem can be checked without disassembling the valve. If you are servicing a flow control valve, check to make sure that the flow control is open. Next, try to manually bleed the valve by twisting the solenoid. This mechanically unseats the plunger from the exhaust port, allowing water to flow out of the chamber of the diaphragm and causing the valve to open. If this solves the problem, the issue is likely with the solenoid. The coil is bad, there is an issue with the plunger, or there is some contamination in the exhaust ports. Unscrew the solenoid and examine the plunger to see if there is debris causing the problem. Check to see if the plunger moves freely up and down, and clean out the exhaust port with a stiff wire. Once clean, check to see whether the plunger rises and falls as the solenoid is energized by the controller. If not, the solenoid is bad and needs to be replaced. Occasionally, there is a problem with the diaphragm or metering system that causes a valve not to open. In this case, replacing the diaphragm assembly should solve that problem. The two main problems associated with pipe and fittings are leaks and water hammer. We'll start by talking about water hammer. Symptom: water hammer sounds like a thump or pounding noise that happens when a valve in the irrigation system closes. The cause of this sound is a shock wave that is created when the water moving through the pipe is suddenly stopped by a quickly closing valve. The kinetic energy in the water bounces off the valve with the thump and sometimes travels back and forth in the pipe, causing a hammering sound after the pipe closes. Because moving water can carry a lot of force, the shock wave can cause damage to the pipe, fittings, and components connected to the pipe. The primary culprit in cases of water hammer is the velocity of the water flowing through the pipes. If the flow rate of the irrigation system is too high for the pipe size, the water can speed up fast enough to cause water hammer. The best way to prevent this is to design the system so that the velocity in the lines is below 5 feet per second. Looking at a sizing chart for PVC pipe, we can see that the chart tells us what the velocity of water will be in different pipe sizes at different flow rates. Keeping the velocity below 5 feet per second is recommended to prevent water hammer. So on the chart, flow rates with velocities above 5 feet per second are shaded in a darker color. If we are using 1-inch PVC pipe, we can see that the maximum flow rate for a zone is 16 gallons per minute, which has a velocity of 4.61 feet per second. If you are having water hammer problems in the irrigation system, you might have an oversized zone that is speeding up the water too much. Suppose you have 6 sprinklers with 3.0 gallon per minute nozzles on a zone with 1-inch PVC pipe. The zone uses 18 gallons per minute and will create a velocity in the pipe of 5.19 feet per second, potentially creating water hammer issues. Re-nozzling the sprinklers in this zone to 2.0 gallon per minute would lower the flow rate for the zone to 12 gallons per minute and would eliminate the excess velocity in the pipe. Another potential solution to water hammer issues is to install slower closing valves. Larger valves close more slowly than smaller ones, so sizing up the valve could solve the problem as well. The other potential solution for water hammer is to try to install a water hammer arrestor behind the valve where the water hammer is occurring. A water hammer arrestor is a mechanical shock absorber that disperses the shock wave, preventing it from traveling any further along the pipe. Symptom: a split or broken pipe, which usually causes a wet spot in the lawn or water visibly flowing out of the ground. Fixing a pipe usually involves cutting out and replacing the bad section of the pipe. Dig up the broken area of the pipe. A common mistake when fixing leaks is to dig the hole too small. Make sure there's room on either side of the break. You'll want to have 12 to 18 inches of pipe visible to work with. When working with PVC, a telescoping coupler, sometimes called a slip fix, can speed up the process. Cut out a piece of pipe long enough to accommodate a slip fix and an additional coupler. First, you'll need to attach the coupler to the telescoping end of the slip fix. Use primer and solvent cement or a one-step cement like Christie's Red Hot Blue Glue. Prepare the ends of the pipe and insides of the slip fix and coupler. Slide the flip fix over one end of the broken pipe and then extend the telescoping end with the coupler so that the coupler slides over the other end of the broken pipe, completing the repair. Repairs in polyethylene pipe can be somewhat easier because the pipe is more flexible than PVC. The pipe can be repaired by inserting a new piece of pipe with couplers. Symptom: leaking water at a threaded connection, on a metal pipe, or in another difficult to repair area where replacing the bad pipe would be cost prohibitive. Sometimes you'll encounter leaks in places that don't lend themselves well to cutting out the damaged pipe and replacing it with a new section of pipe. In these cases, you can use an epoxy-based repair kit like Christie's Slick Wrap to do a wrapped repair. Be sure to follow the instructions on the package as products vary on the specifics of how to use them. You'll need to turn off the water and clean the leaky area of the pipe. Then aptly apply putty to the problem area and wrap it with an activated epoxy resin tape. This creates a watertight seal over the leak. This concludes our course on troubleshooting the mechanical components of an irrigation system: sprinkler heads, valves, and pipes.